Hi everyone. What we're going to work on in today's video is how to sketch the graph of a derivative from the graph of the original function. So I kind of go through a system here. The first thing I like to find is where the slope of the tangent line is 0. So right here I can see at x equals -1, the slope of the tangent line will be 0. So I'm going to drop that right here. And what I want you to notice is that all of these tangent lines would be negative, wouldn't they? So because this function is decreasing, the tangent line would be negative, meaning it's below the x-axis. And from this point to the right, all of the tangent lines would be positive because the function is increasing, so it would be up here above the x-axis. So for right now, we don't really know the slope of the line, and we could certainly figure it out if we knew the equation of this function, but it's just going to look something like this. Okay, now if you did something that was steeper or not as steep, that's fine, because right now we're just estimating and we're just kind of, going from the graph. Okay, I want you to notice that this is a parabola, meaning it's a second degree polynomial, and this is a line, meaning it's a first degree polynomial. Hopefully by now you realize when we take the derivative is always 1 degree less than the original function. So let's go ahead and let's look at the next one. The next one, certainly to me, looks like a cubic function. We have a horizontal asymptote at 0. And 1, 2, halfway between 2 and 3. So I would put those on my x-axis first, 0 and halfway between 2 and 3. This is a third degree polynomial, which means this is going to be a second degree polynomial or a parabola. I want you to notice that it's increasing up until 0, so that's going to be positive, right? All of these tangent lines have a positive slope, so we're going to be up here. Between 0 and that 2.5 mark, all of the tangent lines here would be negative, so it's going to be below the x-axis. And then after that, it's going to be positive because all of the tangent lines here would be positive because the function is increasing. So you're just going to sketch some kind of parabola that shows that. And again, we're not super precise here because we don't know exactly what the function is. Maybe your parabola had a lower vertex. I don't know, but it should look something like that. Let's go ahead and do the third one. Doesn't this look like a fourth degree polynomial? Okay, and by the way, it's a positive fourth degree polynomial. So I look at the zeros. We have a 0 at about -1.5 for our tangent line. We have a horizontal tangent line at 0, and we have a horizontal tangent line at about 1.5. So -1.5, drop a little meatball there. At 0, put a little meatball there, and at about 1.5. Those are the zeros of the derivative. Now, negative, so down here, between -1.5 and 0, all of our tangent lines would be positive because the function's increasing, so we'll be positive here. Between 0 and 1.5, all of the tangent lines would be negative, so we'll be down here. And after that, all of the tangent lines would be positive, so we'll be up here. Fourth degree polynomial, the derivative will be a third degree polynomial. This was a positive fourth degree polynomial. This will be a positive third degree polynomial. This is going to look something like this. And again, it was below, it was above, it was below, it was above, because it was negative, then positive, then negative, then positive. Okay, so far so good, I hope. I want you to stop this video and go ahead and try 4, 5, and 6. Okay, so stop the video, try those 3 problems, and when you start the video up, I will have the answers there for you. No cheating. Stop the video. Okay, let's see how you did. I want you to notice this is a positive third degree polynomial, which results in a positive second degree derivative. Look at your zeros, make sure they match. This one was a negative third degree polynomial, which resulted in a negative second degree derivative. And number 6 was a negative second degree polynomial, which resulted in a negative first degree, which is a line with a negative slope. Okay, let's go to the next page. These are a little bit different. As you may recall, the derivative of a line is equal to the slope of that line. Okay, you also need to remember on these problems that anytime you have a corner or a cusp, you are not able to take the derivative there. So what we're going to do is we're going to look at the slope of this line. So and we typically assume there are arrows at the end of these. So from negative infinity until negative 2, this line has a slope of negative 1. Therefore, the derivative is equal to negative 1. So I'm going to go to negative 2, negative 1, and put an open circle. And the derivative of all of this is negative 1. So the derivative of a line or line segment is the slope of that line. So between negative 2 and negative 1, we have a slope of 1, 2, 3, 4 over 1. So we have a slope of 4. So we go up here, we have an open circle again because we're going corner to corner, and open circle here, slope of the tangent line there would be 4. And from negative 1 to infinity, we have a slope of down 1 to the right 3, so we have a slope of negative 1/3. Again, open circle, we're going to find a height of negative 1/3, and then the slope of the tangent line is constant at negative 1/3. Okay, let's take a look at the second one. Okay, again, we're calculating our slopes. Again, let's assume we have arrows here and here, right, at the beginning, at the end. So from negative infinity until negative 2, we have a slope. Let's look down 1, 2, 3, 4 to the right 1. So we have a slope of negative 4. It's a little bit off my graph here. So I'll go over to negative 2 because that's where I see I'm going to have this open circle. I have this jump discontinuity. So negative 2 and then down 1, 2, 3, 4 would be about here, open circle. The slope is negative 4. Jump discontinuity, so starting here when x equals negative 2 until x equals 0, we have a slope, let's see, 1, 2, 3, 1, 2. So we have a slope at 3 over 2. So 3 over 2 is 1.5. So we have a constant at a height of 1.5. Again, jump discontinuity, so we'll have an open circle when we do the derivative from 0 until 1. And I want you to notice down 1, 2, 3, 4, 5. This is definitely off my grid. So if this was 4, 5 would have been like down here. We'll go into the next graph. We'll have an open circle, and it only goes for a short while. Again, let's assume this is negative 5. My graph wasn't the right size for this one. And then this is interesting because this is the slope this is the line y equals 2. And if we were to write that out in slope-intercept form, this is what it would look like. So the derivative of y equals 2 is 0. And just think about anytime you take the derivative of a constant, it's 0. So here we go, open circle, and height of 0 forever and ever into infinity. You go ahead and try that last one. I'm going to erase this. Don't think it would be in the way, but anyway. Go ahead and try that last one. Stop the video, see how you do, and then check it against my answer. Okay, no cheating. Stop that video. Okay, so how did you do? Hopefully you went through, you calculated your slopes. We don't have jump discontinuity this time, but we have all of these corners, so we certainly can't take the derivative there. We have a lot of discontinuity in our derivative here. And this, of course, is the height of negative 4. Okay, and that'll go to infinity. All right, everybody, have a wonderful day.